Good morning, students. So let's get into the second part of the revision series. Now, I have picked up a couple of learning outcomes from the EOT. One is from the multiple choice, which is number 9, which states the relationship between charge density and the electric field magnitude E, and also specify the direction of the field and so on. So that's on page numbers 47, 48, and 49. This is about the large conducting surface with uniform charge density or etc. Okay. Now coming to this writing part question 3, there are two sections and those pages are from 43 to 46. So you can read the learning objective. So I've just combined all this because it's all under chapter 2.7, 8 and 9. So since it's all combined, I've just taken it together. So this is from your textbook. If you're referring to it, is 2.7, 2.8 and 2.9. I know this 2.9 is something that students find it difficult to comprehend because it is 3-dimension, then surface area, volume, etc. But start from the basics, learn slowly at a time, one step at a time. So make sure you're thorough with the concept, the simple concepts, so that you can build up to the complex ones. Alright, so first let's see what is electric flux and what is Gaussian rule in this session. Now, electric flux is represented by the symbol. We all know it's read as phi, and it is the product of the electric field vector times the area vector times the angle between the two, or it is the dot product. So you have both are vector quantities E and A. So you must think about the direction of the two vectors and apply it in the formula. So theta is important because sometimes we normally take it as EA, assuming that cosine theta is 1. Most of the situations is such, but always remember the formula has got cosine theta as well. Now the second confusion arises when you're trying to find out the direction of the area vector. Now the area vector separately, if you see, it is a line that is normal or perpendicular to the surface. So if you have the surface as horizontal, area vector will be making an angle 90 degrees to the surface. So as you notice here, the yellow or the peach color rectangular sheet, that is your surface. This is your surface. And the area vector is also pointing out of the surface, making 90 degrees to the surface. Alright, the other red lines are marked for indicating the direction of the electric field. Okay, so if you have a flat surface, the area vector will be making an angle 90 degrees to the surface. Right, that is one point that you have to keep it in mind. Now if it's a curved surface, this also will be discussing in many situations where you have a sphere or a spherical shell or a solid sphere, etc. We will be coming across such situations where you need to find the area vector. Now the area vector at any point on a curved surface, especially on the surface of a sphere or a circle, you will notice that it will be making an angle 90 degrees as such. So you can see it's already marked here. So it will make 90 degrees and it comes out of the surface. So that's the area vector. Then you need to compare this area vector with the electric field direction and identify the angle between the two. And you will apply that angle in this theta. So that is about electric flux. Now, they have clearly mentioned in the EOT that you must write units in all these calculations for the writing part, otherwise you might be ending up losing marks. The unit for electric flux is, unit for electric flux phi is Newton meter square per coulomb. Okay, so we know the unit for electric field, that is Newton per coulomb. For area it is meter squared. So combining the three, you get Newton meter square per coulomb. So this is about general electric flux definition, formula and unit we have seen. Alright, now let's apply into some situations. It's a very simple question, but still it's important to identify the direction between the two electric field vectors. Now if you notice here, the sheet is kept in this direction and the electric field vectors are the black lines, and see the area vector is also pointing in the same direction. Now the common mistake or common misconception is students assume that the angle between electric field vector and area is 90 degrees. No, it's not 90 degrees. As you see, the area vector is pointing outside of the surface. Area vector should be perpendicular to the surface. So the angle between area vector and the electric field vector, in this case theta, is 0 degrees. Right? Here it is 0 degrees. And how about in this case? Here again, you need to find out the angle between electric field vector and the area vector, which is theta. It's not 0, not equal to 0, even not equal to 90 degrees. It's somewhere between 0 and 90. Now coming here you have the area vector theta is equal, the angle theta is 90 degrees. So if, for example, the electric field is given as 2.25 times 10 to the power of 5 Newton per Coulomb, and the area of the sheet is given as 1.1 meter square. If you're asked to find out phi for each one of these, so for part 1 for this, okay, phi equals EA cosine theta. So it is 2.25 times 10 to the power of 5 times 1.1 times cosine 0 degrees. Now cosine 0 is 1, so you get the answer to be 2.48 times 10 to the power of 5 Newton meter square per Coulomb. So it's not a difficult question, not a tough question. Only thing is that you need to find out the angle between the two, area vector and electric vector. Now for the second part, phi is EA cosine 90 degrees. So cosine 90 gives you 0. So since all these are product, the entire factor or the entire equation becomes 0. So that's about it. So, oh sorry, not this second, it's third one. Third one is 90 degrees, so it becomes 0. Okay. And here, if the angle was given any angle, assume it's 45 degrees. So if you substitute for the second part, you will substitute E times A times cosine 45 degrees and get the answer. Alright. So these are simple ones. Definition for electric flux, because they mention here, define the electric flux through a surface as the dot product between the electric field vector and the area vector at each point. Okay, so they may ask the definition of electric flux. That's why I insisted on that. Okay, so that's like a snapshot of the entire thing. Formula, angle, if the angle is 0, you just get E times A. If the angle is 90 degrees, you get 0. Okay, now we solved this equation earlier. So that was an example question we just solved. Okay. Now we have seen in the previous section about electric flux, its unit, definition, formula, and application of the same into a question where you were asked to find out the flux for different dimensions of the surface. As I mentioned, the tricky part is to find the area vectors, the angle between area vector and electric field vector. Now this segment we will see about the Gauss's law, because as you can see in the learning outcome, it's mentioned. Even all these together, we will see it in this session. Okay. So what is Gauss's rule? All of you might know it is for a closed surface. So it's an important clause in applying Gaussian rule or Gaussian law is the closed surface. So you cannot apply it to any other situation other than a closed surface. the phi or the electric flux equals Q over epsilon naught. Now this is the formula that will be given in your formula sheet, but I would want you to remember this Q as it's an enclosed charge. So the charge enclosed inside the sphere or inside any closed surface. So it can be written as Q enclosed, or it could also be remembered as Q net. So you find the total charge enclosed in the surface, you find the total, or you find the total net charge inside the closed surface and apply it in the formula. And the value for epsilon naught again will be given in your formula sheet, which is 8.85 times 10 to the power of negative 12, which is a constant. So that is about Gaussian rule. You can learn the definition as given in the textbook, or I'll be giving it at the end of this video. Learn it, please. Now, we can derive the same because they are mentioned here, dot product at each point, and expresses that in an equation. Okay, so let's go through how to combine Coulomb's law, or from Coulomb's law, how can you derive the same formula? Okay, we know that the Coulomb's law for electric field is given by 1 by 4 pi epsilon naught times Q over R square. Now, you might be aware that K equals 1 by 4 pi epsilon naught. Okay, so this, you may remember this as this is also equal to KQ over R square, but we are using this because we have in the Gaussian rule epsilon naught, so we have expanded the Coulomb's law by using K equals 1 by 4 pi epsilon naught. Now taking the basic formula for phi equals A times cosine theta. Now here, since we are taking for a closed surface, let's assume that we have seen in the previous session that the angle is always 90 degrees. If the electric field is coming out, it's going to be positive. It's going in, it's negative. So we have the angle to be 0 degrees. So this becomes E times A. Alright. So the closed surface integral, if you integrate the entire area for the electric flux and area, this should be equal to the Coulomb's law equation, which is 1 by 4 pi epsilon naught times Q over R square. So writing the equation for electric flux phi equals E times A times cosine theta, and as we know, the angle between the electric field vector and the area vector is 0 in the curved surface, so this can be applied to 0, and E times A is the total integration of the area times cosine 0. Okay. So the total area for this, it's a surface area of a circle, which is, so surface area of a circle is a formula from math, it's 4 pi R square. Okay, so we substitute that area, this is area, so this area we substitute in the formula. For E we substitute this formula, which will simplify to, so 4 pi epsilon naught times 1 over R square times the area is 4 pi R square. Okay, let's cancel out the common terms. So we have 4 gets cancelled, pi gets cancelled, R square gets cancelled. So sorry, this is Q, not on, this is Q. So all these other factors get cancelled and you are ending up with Q over epsilon naught. So this is combination or deriving Gaussian rule by using Coulomb's law and the basic formula for electric flux. So we end up with the same formula for a closed surface. So for a closed surface, the electric flux is equal to the Q net, the charge enclosed, over epsilon naught. Now for the next segment, you need to, before applying different situations symmetry or a closed surface for solid sphere, spherical shell, flat, as in the learning outcome you can see for a closed surface, real or imaginary, and also here for a conducting surface, etc. You need to bring in something that you learnt before about the charge density. Okay, so using the charge density formula and the combination of electric flux and Gaussian rule, we can derive different formulas or expressions for electric field. That'll be the next session.